All right, hello everyone, and welcome to my channel. This is an educational channel, and we look at great theories of everything from the recent past and the ancient past, and try to make sense of them, see if they can help us out with our. Sorry, I'm a bit preoccupied here. Something fell. Help us with our formation of paradigm, new paradigm, with our awakening to 5D consciousness and or our adaptation of a adaptation of our holistic worldview. And today is our 499th video that we've done on the reciprocal system of theory. I believe I announced the wrong number yesterday, but I believe today is number 499. And the reciprocal system of theory was arrived at by Dewey B. Larson and articulated when he put out his two fundamental postulates in 1959. For the remaining 31 years of his life, he first derived a theoretical universe, what his universe would look like if his postulates were correct. And then in many books, he compares his theoretical universe with the measured empirical universe of the legacy scientists. And we're looking at one of those books today called Basic Properties of Matter. This is a book that's on chemistry. We are in chapter 16 of that book called Induction of Charges. And in this book, Larson arrives at equations, expressions for many of the basic properties of matter, like the melting point or the compressibility or the specific heat. And then he compares them with the scientific tables already extant. And in many cases, he's able to basically recreate the scientific tables strictly from theory. So that lets me know that the theory, there's either something to the theory or he's fudging the numbers. And just from reading Larson, reading many of his books, I just don't think that he's going around fudging the numbers systematically like that. Now, in this case, I think he actually might be fudging some of the numbers unconsciously, where he thinks he has the correct expression, but he doesn't. But he kind of does some contortions in order to convince himself that he does. So, Larson admitted that he was not without error, but I don't believe he was malicious in what he was doing. He just kind of deluded himself into thinking that he has the right expression for some of these electrical quantities, in particular capacitance. That's kind of got him off track here, I think, with some of his electricity and magnetism stuff. But I could be wrong. He could be right about all this, but some of Larson's associates have also, expressed concern about his assessment of units in particular with capacitance and with many other aspects of his electrical theory. Now, Larson's theory, his two fundamental postulates and its ramifications, I've outlined in much more detail in any of my first 474 videos on this subject. So you might want to take a look at those, because we're trying to turn some pages of this chapter here today, and so I'm not going to get into all the ins and outs of the postulates and how the reciprocal system operates. I'm going to pretty much assume that you have at least some kind of working knowledge of the reciprocal system before you start in on this video. So we're going to start up here. I'm just going to read the last couple sentences of this previous paragraph and then move on to the next. Now, I will give you the first fundamental postulate of Larson, which is where most of the work is done for his theory, that is that the universe is composed entirely of one component, motion. Not matter, not energy, but motion. Existing, that's my parenthetical there, but back to Larson, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, and in particular, Larson is referring to not just any kind of motion, but scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion using a balloon. And if you put dots on it with a magic marker and blow up the balloon, all the dots will be moving away from each other, but in no specific direction. Every dot will be moving away from every other dot. So every dot will be moving in every direction, outward. And if you contract the balloon, then every dot will be moving in every direction, inward. Larson refers to the first as the progression, and he refers to the contraction of the balloon as gravitation. So even though he uses the term the progression is basically the source. This is the source for all manifestation in this universe, but it is not manifestation. So this is the empty universe, the progression. And manifestation comes from reversing the outward motion of that balloon and turning it into inward motion and gravitation, which is inherent in all manifestation of matter. It also is potentially instructive to, instead of thinking of it as the progression, you can also think of it as anti-gravity. It is the kind of the opposite movement to gravitation. So you can think of it as that is the natural state of the universe, is to for everything to blow apart, outward, and that in order to manifest anything, that motion needs to be reversed. Okay, now let's get into chapter 16 here on induction of charges. I'm taking over right in the middle of the paragraph just to remind ourselves where we're at here. But this is not true of the rotational vibration that constitutes a charge. Important to remember that in Larson's system, an electron is uncharged in its natural state. That is what he calls electric current. Electric current is uncharged. An electron, just like everything else in Larson's system, is a kind of motion. And in Larson's system, an electron is a rotating unit of space. And an electron can take a charge, just like an atom can take a charge and a subatom can take a charge. But that charge is not an electron. They're not the same. A charged electron is manifest as static electricity. And this charged electron takes a charge, and a charge is, just like everything else in Larson's system, a kind of motion. A charge is a rotational vibration, which looks like that. And an electron can take one of those things and become charged. So that's what he's referring to here. But this is not true of the rotational vibration that constitutes a charge. In this case, the relation of the motion or the charge to the distant atom is continually changing. That is, the relative motion of the two atoms has the same vibratory character as the charge itself. As has been stated, a scalar motion A, such as a charge, toward or away from atom B, is indistinguishable from a similar motion of B toward or away from A. And that evidences evinces or whatever the mutual nature of scalar motion. A charge of A toward or away from B is indistinguishable from a similar motion of B toward or away from A. The representation of this motion in the spatial reference system can therefore take either form. Ordinarily, some redistribution of energy is required for a change from one representation of a motion to another, and such changes therefore do not usually take place in the absence of external forces. In fact, Newton's first law of motion requires a motion in the direction AB to continue in that direction indefinitely unless acted upon by some force. However, there is an exception to this general rule because of the existence of a class of phenomena that we may call zero-energy processes. Most of the physical processes that have been examined in the preceding pages either operate by application of energy or occur spontaneously with the release of energy. For instance, there is a force of cohesion between the atoms of a solid, and energy must be applied to separate them. If they are allowed to recombine, a corresponding amount of energy is liberated. But the various components of a combination of basic motions are not bound to each other in this manner in all cases. Often they are merely associated and are free to separate or combine without gaining or losing energy. One such zero-energy process is the simultaneous creation or destruction of charges of the same magnitude and opposite polarity. It is the existence of this process, together with the equivalence of scalar motions AB and BA, that makes the induction of electric charges possible. As we saw earlier, all material objects contain a concentration of uncharged electrons, which are essentially rotating units of space. In each case, where an electron exists in an atom of matter, an atom likewise exists in the unit of space that constitutes the electron. This might be compared to a solution of alcohol in water. The atoms of alcohol exist in the water, but it is equally true that the atoms of water exist in the alcohol. Let us now consider an example in which a positively charged body X is brought into the vicinity of an otherwise isolated metallic object Y. And Larson uses the asterisk on positive or negative because he's using the conventional terminology, but he finds that in his system, the negative is a positive and the positive is a negative. But he's using the conventional terminology. The scalar direction of the vibratory motion, the charge, of atom A in object X is periodically reversing. And at each reversal, the reference point of the motion of A relative to any atom B that is free to move is redetermined by chance. That is, the motion may appear in the reference system either as a motion of A toward B or a motion of B toward A. By means of this chance process, the motion is eventually divided equally between AB and BA. An atom C that is located in extension space is not free to move because energy would be required for the motion. But atom B in object Y, which is located in electron space, is not subject to this energy restriction, as the rotational motions of the atom and the associated electron are oppositely directed, and the same motion that constitutes a positive asterisk charge on the atom constitutes a negative asterisk charge on the electron, because in this case it is related in a different reference point. It is related to a different reference point. The production of these oppositely directed charges is a zero energy process. It follows that atom B is free to respond to the periodic changes in the direction of the scalar motion originating at A. In other words, the positive asterisk charge on atom A in object X induces a similar positive asterisk charge on atom B in object Y, and a negative asterisk charge on the associated electron. The electron is easily separable from the atom, and it is therefore pulled to the near side of object Y by the positive asterisk charge on object X, leaving atom B in a unit of extension space and with a positive asterisk charge. The positions of the positively asterisk charged atoms are fixed by the interatomic forces, and these atoms are not able to move under the influence of the repulsive forces exerted by charged object X, but the positive asterisk charges are transferred to the far side of object Y by the induction process. The residual positive asterisk charge on atom B induces a similar charge on a nearby atom D that is located in electron space. The electron at D, now with a negative asterisk charge, is drawn to atom B, where it neutralizes the positive asterisk charge and restores the atom to the neutral status. This process is repeated, moving the positive asterisk charge farther from object X in each step until the far side of object Y is reached. Where the original charge on object X is negative asterisk, a negative asterisk charge is induced on the electron associated with atom B. This is equivalent to a positive asterisk charge on the atom. In this case, the negatively asterisk charged electron is repelled by the negative asterisk charge on object X and migrates to the far side of object Y. The residual positive asterisk charge on the atom is then transferred to the near side of this object by the induction process. If metallic object Y is replaced by a dielectric, the situation is changed, because in this case, the electrons no longer have the capability of free movement. The induced charge on the atom and the opposite charge on the electron, or vice versa, remain joined. It is possible, however, for this atom to participate in a relative orientation of motions with a neutral atom electron unit with which it is in contact, the result being a two-atom combination in which the negative asterisk pole of one atom is neutralized by contact with the positive asterisk pole of the other, leaving one atom electron unit positively asterisk charged and the other negatively asterisk charged. That is, the charge is on the electron. The optimum separation between the unlike charges when under the influence of an external charge, the condition that is reached when the carriers of the negative asterisk charges are free to move, is the maximum. The situation in the two-atom combination is therefore more favorable than that in the single atom, and the combination takes precedence. A still greater separation is achieved if one or more neutral atoms are interposed between the atoms and the charged combination. Each event of this kind moves either the positive asterisk or the negative asterisk charge in the direction determined by the inducing charge. Thus, the effect of an inducing charge on a dielectric is a separation of the positive asterisk and negative asterisk charges, similar to, but less complete than, that which takes place in a conductor, because the length of the chains of the atoms is limited by thermal forces. On the basis of the foregoing explanation, the charges are produced by induction. The subsequent separation is accomplished by action of the inducing charge on the newly produced induced charges. Conventional theory of dielectrics is based on the concept of the nuclear atom, a hypothetical structure in which the components are held together by the attraction between positive asterisk and negative asterisk charges. It is assumed that these charges have a limited amount of freedom of movement and can separate slightly on being subjected to the effect of an external charge. One observation that has been interpreted as supporting the assumption that pairs of positive asterisk and negative asterisk charges are always present in the atoms is that if a charged dielectric is subdivided, each of the parts contains both positive asterisk and negative asterisk charges. This is quite different from the behavior of charges in conductors. If a metallic object is cut perpendicular to the line of force while under the influence of an inducing charge, the two parts are oppositely charged and will remain so after the inducing charge is removed. But if the same procedure is followed with a dielectric, both parts have positive asterisk and negative asterisk charges on the opposite sides, just as in the original object before separation. And when the inducing charge is removed, both parts revert to the neutral status. The current interpretation of these results, as expressed in a contemporary textbook, is this, quote, "The inference to be drawn is that insulators contain charges which can move small distances on that attraction. The inference to be drawn is that insulators contain charges which can move small distances so that attraction still occurs, but that they are bound in equal and opposite amounts so that no splitting of the body can separate two kinds of charge." End quote. The amount of separation of charges that could take place in the manner assumed by this theory is admittedly very small, and it is difficult to account for the generation of any substantial attractive or repulsive forces by this means. But forces of this nature actually do exist. Small static charges, usually produced by friction, are common in the terrestrial environment, and they produce effects that are quite noticeable. Merely walking across a carpeted room in cold, dry weather can build up enough charge to give one an uncomfortable sensation when he touches a metallic object and discharge occurs. Likewise, the behavior of the modern synthetic fabrics shows the effect of static charges, including the inductive effect, in a conspicuous and often annoying way. These fabrics behave in much the same way as charged conductors. They attract such things as bits of paper and chips of wood, and are themselves attracted by the furniture and walls of a room. The discrepancy between the very small theoretical separation of charges and the relatively large inductive effect has forced the theorists to call upon collateral factors, such as the presence of contaminants, to explain the observation. For example, the following statement taken from a physics textbook refers to the ability of electrically charged, non-conducting objects to pick up bits of paper and wood. Quote, "A chip of perfect insulator would show hardly any effect, but bits of wood and paper always have enough moisture to make them slightly conducting." End quote. The much greater separation of charges that results from the inductive process described in this chapter resolves this problem, while it remains consistent with the appearance of charges at both ends of each piece when a dielectric under the influence of an inducing force is separated. Before the separation takes place, a substantial number of atoms of the dielectric exist in multi-atom combinations with positively and negatively charged ends. Although the separation of the charges in many of these combinations is large compared to the distance between atoms, it is very small compared to the dimensions of an ordinary charged dielectric. Thus, when the separation occurs, there are charged combinations of this kind in each portion. Consequently, each piece has the same charge characteristics as the original unbroken object. It was pointed out in Volume 1 that the existence of positive and negative charges in close proximity, as required by the nuclear theory of the atom, is incompatible with the observed behavior of charges of opposite polarity. These observations show that such charges neutralize each other long before they reach separations as small as those which would exist in the hypothetical nuclear atom. This is a decisive argument against the validity of the nuclear theory. It is appropriate, therefore, to note that the existence of both positive and negative charges in objects under the influence of inducing charges does not conflict with our finding that there is a minimum distance identified as the natural unit of distance, 4.56 times 10 to the minus 6 centimeters, within which charges of opposite polarity cannot coexist. The coexistence of induced positive and negative charges is possible because they are forcibly prevented from reaching the limiting distance at which they would combine. If the external charge is removed, the inducing charges do combine and neutralize each other. In charging by induction, it is often convenient to make use of grounding, which is simply connecting the inductively charged object to the earth by means of a conductor. The earth is electrically neutral and so large that it is insensitive to gains or losses of charge in the amounts actually encountered in practice. If object Y is grounded while under the influence of a negative asterisk inducing charge, the negatively asterisk charged electrons on the far side of the object are forced through the conductor into the earth. Breaking the ground connection then leaves only positive asterisk charges on object Y, and this object remains positively asterisk charged after the object X that contains the inducing charge is removed. If the induction process is initiated by a positive asterisk charge on object X, the ground connection that permits the electrons to be pulled from the earth and charged negatively to neutralize the positive charges on Y, leaving only the positive, let me start with that sentence again. There's too many asterisks here. If the induction process is initiated by a positive asterisk charge on object X, the ground connection permits electrons to be pulled from the earth and charged negatively asterisk to neutralize the positive asterisk charges on Y, leaving only negative asterisk charges. Breaking the ground connection then leaves Y negatively asterisk charged. Okay, I think we're gonna stop right there for today, and we've still got a ways to go on this chapter. Hopefully we can finish it tomorrow. I will also comment a little bit tomorrow about the nuclear atom. Larson's atom, he has a book that's called The Case Against the Nuclear Atom. Larson's atom does not have a nucleus. The atom itself is the nucleus. So the space between the atoms, that electron cloud is nullified in Larson's system. That is really what he calls the interatomic distance. Maybe I'll comment on that tomorrow also.